Hello, today we're going to be talking about chemical reactions, last part of the section from chapter 19, sections 1 and 2. First thing we need to know about chemical reactions is that there's energy involved, so the energy and the reactions. Remember, chemical reactions change the subject you're working with into a new substance. We're not talking about mixtures here, which there is no reaction. We're talking about a chemical reaction, a chemical change. For instance, when baking soda and vinegar are combined, they create carbon dioxide, acetic acid, and water. The baking soda and the vinegar have been changed into completely new substances, and that's how you know it's a chemical reaction. For example, burning, color changes, fizzing, foaming, odor changes, rusting, these are all signs of a chemical change. We talked about this a couple months ago when we talked about the difference between chemical changes and physical changes. Chemical reaction that happens always has two parts. You have a reactant, that's what goes into the reaction, and you have the products. These are the new chemicals that are formed in the reaction. Okay? So in our example above, when we had the baking soda and vinegar combining, what were the reactants and what were our products? One of the things that we're going to talk about now is splitting water. So when electricity is see in our chemical formula here, H2O, we have this arrow. This shows the chemical reaction and it yields. So reactants are on the right, the left, and the products are on the right. The products are hydrogen gas and oxygen gas. But do we have equal parts hydrogen and oxygen? If we look, notice in the products we have two hydrogen molecules forming H2 and two oxygen molecules forming O2. But if we look at the molecule at the beginning of our reactants, we only have one oxygen molecule and two hydrogen molecules. So it's not a balanced equation. So therefore, in order to do this, we have to make sure that the same amount of reactants and products are on the same side. First thing we want to talk about is a chemical equation. This is a use of symbols to show how the chemicals react. Again, like I said before, the arrow, this means turns into, it separates the reactants from the product. Remember, the law of conservation of mass says that whatever amount you start with in a reaction, this is the amount that you have to end up with, which is why we balance chemical equations. The chemical formula, remember that breaks down into individual components. Even though there are parentheses around it, there's one phosphorus and four oxygen in that one. Now notice if the number is outside of the parentheses, we multiply all of the elements, all of the atoms inside by that number that's on the outside. All right, so this phosphate now has been multiplied, so we have 3 phosphorus and 12 oxygen. All right, so just remember that. That's the number one thing that people mess up on when they're trying to balance equations is that you multiply it by the outside number. All right, here are some rules for balancing equations. The same number of atoms have to be on each side. You can't have 4 on one side and 2 on the other. Okay, you have to have the same number of atoms on both sides. If there are different numbers on each side, you can only add atoms to balance the equation. You can never take anything away when you're balancing chemical equations. You can only add to it. Gases are always bonded together. Hydrogen, oxygen, fluorine, nitrogen, chlorine, iodine, and bromine. These are all gases and they are diatomic, okay, which means there are 2 of them. So chlorine gas is Cl2, so on and so forth with all the other ones. So just remember that gases are always bonded together. They're diatomic. Also know that you can never change the subscript. You can never change that little 3 down there below the phosphate parentheses. You can only change the coefficient, which is the number in front. And we'll have lots of practice on this. Okay. Remember, reactants are on the left of the arrow and products are on the right. Okay. 1Na plus chlorine gas, right, equals sodium chloride. But you notice it's not equal. So the only thing we could do is put a 2 in front of our sodium. So 2 sodiums and 1 chloride gas yields 2 sodium chloride molecules. Okay. All right, so here we're going to balance chemical equations. So the first thing you want to do is write each element down and how many of each atom that you have. You look at your equation and then you change your coefficients, which are the numbers, the gaps that are in front. That's what you change back and forth. Make sure when you're done you recheck how many atoms of each element you have, and then cross out your old numbers. And you're going to sometimes go back and forth on either side of your arrow, depending on how long it takes to balance everything out. If the amounts are equal on both sides, you're done. If not, you need to change the coefficients again. We'll have lots of practice with this. For example, here is iron and chlorine. Notice that iron is by itself, but chlorine is a gas. So there's two of them, but when they combine in a reaction, they yield iron chloride, right, with 3 chloride atoms. So therefore, we know right away 2 and 3 don't match up, so we need to multiply by the common denominator. Okay, and we'll have lots of practice with this. Here again, some more examples, some different reactions. You can take some time and work through them on your own if you'd like. So chemical reactions, there are 5 basic types of chemical reactions. And these are very important to know. In the chemical reactions, remember the arrow means produces, turns into, or yields. That arrow shows the difference between the reactants and the products. So the first chemical reaction we're talking about is a synthesis reaction. These are where atoms are combined. Notice we have sodium, we have chlorine, we combine them to sodium chloride. This is a synthesis reaction. The next type of basic chemical reaction is a decomposition. This happens when atoms are broken apart. For instance, if we take water and break it into hydrogen gas and oxygen gas, that is decomposition because you can see the atoms coming apart and the compound breaks into atoms, okay? The opposite of synthesis. The next type of chemical reaction is a combustion reaction. This uses oxygen to ignite substances, which will always have oxygen by itself in the reactants. As you can see here, we have methane and we have oxygen. They combine and make carbon dioxide and water. So the oxygen has been combined with our other 2 compounds here. So this is a combustion reaction. It has oxygen by itself, right, being added to something else. The fourth one is called single displacement. This is when one element switches, takes place of another. I like to talk about it. It's the ever-present girlfriend who decides to switch and go date the friend. All right, so AX is together plus B. We have our reaction, and now B is now with X, and A is by himself. Okay. The example here shows copper chloride and aluminum. After the reaction, the aluminum goes out with chlorine, and our copper is all by itself. And the last one we talk about is double displacement. That's when 2 couples decide they don't like each other and they swap. All right, so this double displacement, 2 elements swap places with each other. AX plus BY yields AY and BX. It's a double displacement. Okay. An example for this, all right, shows here they basically switch all of the partners. Okay. So here are some examples for you to kind of pick through. Remember, if oxygen by itself, all right, oh, you might be thinking this is a combustion. However, notice that it's the other reactant is just hydrogen. So it's not a combustion. This is a synthesis. 2 individual elements are joined together in a compound. All right, and then we have a decomposition, right? A compound is broken down into individual atoms. And so on and so forth. The last thing we'll talk about today is oxidation and reduction reactions. Remember, oxidation is all about the loss of electrons. And the reason we call it oxidation is because oxygen, right, is very reactive and it pulls electrons away from the rusting iron. So iron is typically kind of, and it rusting iron oxide is kind of where they first really did a lot of the research and they came up with these terms. So oxidation pulls electrons away. Okay. Reduction, right, is the gain of electrons. It seems kind of opposite. You'd think, well, if you're reducing something, you'd lose something. But remember, electrons are a negative charge, so you're actually reducing your positive charge. Okay. So a reduction is a gain of electrons. Right? An oxidation loses electrons. As a substance gains more electrons, it becomes more negative or reduced. Okay. And these reactions are always paired. You never have something just losing electrons out there. The electrons have to come somewhere. So these reactions we typically call redox reactions, where it shows basically the movement of electrons back and forth. And this is very similar to like electrical flow. Like for instance, if we were to construct a voltage pile, make a battery with pennies and washers, zinc washers, they're going to pull electrons back and forth from each other. And this would be an ox-redox reaction.